All right, so now we're going to give our explanation as to why a conjugated set of pi bonds is more stable than isolated pi bonds using molecular orbital theory. So just to remind what the heck molecular orbital theory is, we talked about it a little bit last semester, but let's again just take our ethene as an example here. Okay, ignoring the sigma bonds for a second, I mean, the principle sort of applies there as well, but focusing in particular on the pi bonds. We have these sp2 hybridized carbons, which means that they have one leftover p orbital each. And when this compound first forms, each one of those p orbitals is housing one electron. Well, why don't they just stay where they are, right? Why do they form pi bonds to begin with? So this is what we call molecular orbital theory, which is this idea that atomic orbitals will mix to form molecular orbitals. So in particular, in this case, we have two atomic orbitals that are mixing to form two new molecular orbitals. In general, the number of atomic orbitals that you mix will equal the number of molecular orbitals generated. Okay, so these two p orbitals mix. So notice over here we have energy on our y-axis. Here is the energy of those two p orbitals when they're all by themselves. We can even sort of like color code this green carbon here. I'm talking about that's his p orbital when it's all by itself. And this pink carbon, this is his p orbital or her p orbital when they're all by themselves. Right? So they're sitting at this energy. Well, when they mix, they generate two new orbitals. That would be this pi star orbital here and this pi orbital here. Notice that one of those new orbitals, new molecular orbitals, again, these are the atomic orbitals mixing to form molecular orbital. One of the new orbitals that's formed is lower in energy than the original atomic orbitals, and the other one is higher in energy. This one we sort of label pi star because it's what's called an anti-bonding orbital. So then we had these two electrons that each one of these brought to the table. Again, our green brought this, and our pink brought this electron. And when these two new molecular orbitals are created, both of them are going to start to occupy the molecular orbitals by first occupying the lowest, going up. Okay, so what we have is that this is this electron, and this is this electron, and then we've run out. So our anti-bonding orbital isn't occupied at all. Okay, so notice that the new orbital that's been formed and is now occupied is this pi molecular orbital that is lower in energy than the two atomic orbitals that we started out with. Okay, so that's why pi bonds, not even talking about conjugation, that's why pi bonds form in general. And that's why all sort of bonding orbitals form. It's because you have atomic orbitals that come together and form new molecular orbitals. As long as the anti-bonding orbitals aren't filled, right? If we had more electrons, then our anti-bonding orbital would be filled, then it wouldn't happen. But since that isn't the case, that's why this is a favorable interaction. So now let's extend this to this idea of having 4 p orbitals. So now I'm talking about looking at a compound like 1,3-butadiene. Each one of these has a p orbital that it's bringing okay, and so this is going to be this molecular orbital concept that you're going to have 4 atomic orbitals that you're going to create, that you're going to mix, and that's going to give you 4 new molecular orbitals. Okay, so this is kind of different than this picture that we get by drawing the stick figure, where we look at that and we say, oh, I have 2 pi bonds. This is now this theory where we're going to take all these orbitals, we're going to mix them all together and see what molecular orbitals come out. Mix all those atomic orbitals. And what we get in our conjugated network is we now have this lowest energy molecular orbital where all 4 of those p orbitals are bonded together. It's like as if there was one giant pi bond that existed across that whole molecule. Now, each one of these had an electron that they brought to the table. So that's 1, 2, 3, 4, which means that we're going to not only fill that lowest energy orbital, this one here, right? Those are those 2 electrons filling that one, but we're also going to fill the next layer up. And here you'll notice that every layer up you go, you gain a node, which is sort of this this line that the electrons can't jump across. And now this looks much more like an isolated diene, okay? So this would be our isolated, this is now conjugated, but because both of those orbitals are filled, they're both sort of true at the same time. So that's why butadiene doesn't just behave as if it has 2 isolated pi bonds, it also has this conjugated character as well. And then we go one level up, we now have 2 nodes. This is now unoccupied, which is great because it's actually higher in energy than the p orbitals when they're all by themselves. Or we could go all the way to this highest energy molecular orbital here, where there are 3 nodes. This is basically as if all 3 of those p orbitals weren't talking to one another at all. Another sort of way to draw this without the stick filling or the space filling atoms in between is just to show these pi bonds. These p orbitals, and the conjugation is shown. The red and the blue is phase, what we call phase. Electrons, this is kind of this annoying thing where in organic chemistry, you don't know quantum mechanics yet. So we kind of just have to like lie to you a little bit about what's going on, or we can't give you the full truth. The bottom line is electrons have something called phase, where some of them will be positive. The positive ones can interact with one another favorably. The other ones have this phase negative. The negative ones can interact with each other favorably. Positive and negative can't interact, right? So when we go one layer up, again, this is if we just had isolated dienes. Notice that these p orbitals, they're obviously still sitting right next to each other. The difference is the phases of the electrons that occupy them, okay? I know this is kind of confusing. The bottom line is that these 4 atomic orbitals will mix together to form one new low energy molecular orbital that's occupied. Well, it'll form 4 molecular orbitals. One of them is really low energy and it's going to be occupied. And that's the one where the electrons can travel all throughout that network of conjugated p orbitals. And this is sort of what I was saying before with regard to, again, this is sort of, if we looked at butadiene here, we of course know that this is a pi bond and this is a pi bond. What molecular orbital theory tells us is that there's actually a molecular orbital that's occupied where there's kind of a bond, a pi bond located between these 2 as well. Okay, this is one of these things where we can't really accurately draw it perfectly using our stick figures. That's why we go through the trouble of being able to spot conjugated pi bonds. But the thing that's so special is, again, that those electrons are jumping, the electrons that are in this pi bond here are able to jump over into this network here, going through the middle there. And that's because of this lowest energy molecular orbital, where all of those p orbitals are in phase with one another. So all those electrons can pass freely back and forth. The other this is actually the HOMO, the highest occupied molecular orbital. That has 1 node, and that behaves where there's no double bond character between, carbons 1, 2, and 3. Okay, so bottom line is, these orbitals do kind of crazy things. This is why picturing electrons not as particles, but as clouds is really important. So now focus on being able to kind of draw this yourself, right? So now let's take something that's even more complicated. 135 hexatriene. Okay, how many atomic p orbitals am I going to be mixing? 6 atomic orbitals. So then how many molecular orbitals should I get out of there? There should be 6 molecular orbitals as well. Half of them, so this is the energy of p alone. Half of them Molecular orbital 1, molecular orbital 2, molecular orbital 3 are going to be lower in energy than P by itself. And the other half, 4, 5, and 6, these are our anti-bonding orbitals. Those are going to be higher in energy than the P alone. Again, importantly, since each one of these P orbitals had an electron to bring to the game, that means that I'm going to fill in these molecular orbitals with 6 electrons. So that's why only the bottom 3 get filled. Okay, so now in terms of what these look like, if we're going to picture these, remember, what's the lowest one going to look like? What should I draw for my lowest energy molecular orbital? That's going to be the one where the electrons can pass freely throughout the whole deal, right? So that's when all 6 of those P orbitals are in phase with one another. They're all lined up and their phases are lined. Now, every time I go up in energy, I'm going to have to introduce a node. So that means when I get to molecular orbital 2, I have 2 sets of orbitals that are sort of in phase with one another with a node between them, right? Go up one more level, what am I going to have to introduce? Another node. And so this is where we sort of have in molecular orbital 3 is when all of those double bonds are acting sort of independently as if they were isolated. But again, because all 3 of these molecular orbitals are occupied, they're all 3 true at the same time. I know that you probably are like, what the hell does that mean? It just means that I have 2 electrons occupying this space where they can go freely. I have 2 electrons occupying it where there's, as if there's just 2 gigantic pi bonds going on. And then I have 2 electrons occupying to where they're individually spaced, or rather they're isolated. So now I'm going to introduce another node. Notice that I'm going to chop the ends off so that I have my 2 ends that are out of phase with one another and kind of broken away from the group. Introduce another node, and then finally my highest molecular orbital, highest energy molecular orbital is when I have 5 nodes. So every single one of those P orbitals are out of phase with one another. Okay. Now, in terms of the interaction between matter and light, we were talking about this before with our spectroscopy. In particular, right, I drew my really well-drawn light bulb where I had photons coming out of it. Those pass through a sample. Some of those photons are absorbed, some of them are not, and I can measure that by what hits my detector. What exactly is happening during this absorption is that an electron is jumping from the highest occupied molecular orbital, right? So that's, if you just sort of break down the name, highest occupied molecular orbital, that's the one that's the highest in energy, but still has electrons in it. And it's going to be bumped to the lowest occupied molecular orbital. So let me actually clean this up a little bit. Get away, you designations, from now. Just to be sort of kind of clarify what happens real quick. So when I have my, this is again, (1,3,5) hexadiene. When I have my hexadiene in my sample, I shine light at it. What happens is that it absorbs a photon. What that really means is that that photon kicks that electron from the HOMO to the LUMO. Okay, so as a result, now my HOMO, my highest occupied molecular orbital, is actually one of my anti-bonding orbitals, and my lowest unoccupied molecular orbital is going to be that next level up. What happens from here, this electron will relax back down and release either light or heat in the process. Okay, but that's why these dienes, really why anything, are absorbing light, is because you're knocking an electron from the highest occupied molecular orbital up to the lowest unoccupied molecular orbital. So just using these MO diagrams that we just learned how to draw, we can illustrate that process.